All right, so today we're going to talk about volumes of known cross sections. So basically we have some 3D objects can't be thought of as nice geometric solids or revolved about a line to get nice volume formulas. But we could slice them up so that we can find similarly thinly sliced shapes, and then summing all of those areas up of all the slices, we'll find the volume. So that's kind of what we did with our project for the last couple of days, was to build models like that in order to be able to find the volume. So today we're going to just kind of jump right into finding those volumes. So for example 1, we are supposed to find the volume of the solid that lies between planes perpendicular to the x-axis at x equals 0 and x equals 2. The cross sections are semicircles and are perpendicular to the x-axis and run from y equals the square root of x to y equals 0. So if I sketch a quick little diagram of what this is going to look like, I know a square root function looks something like this. And so I'm picturing little semicircles where all what I'm seeing, I'm just seeing the base because the semicircles are sticking up off of my paper at me. Kind of like something like this. See where they kind of stick up off the paper at us? Where we glue them in. So that's kind of like what it looks like. So first question I always ask myself so I don't get confused or lost is, what is the shape of the cross section? So going back through, I notice they're semicircles. All right, so then the next thing is I'm like, okay, so I look at my diagram here and I go, okay, so what does each of these rectangles represent? So each rectangle, if I go back to my model, so each of those rectangles, that's like the base, right? So each of those rectangles would be the diameter of my semicircles, right? Each rectangle is the diameter of the semicircles. All right, so the next thing I want to know is, what is the length of the diameter? So I want to know, how do I figure out what this length is? So this kind of goes back to, okay, so I know to find this length, I'd go from the top all the way to the bottom. So that would be the square root of x minus 0. So I just get the square root of x. So that would mean the diameter for my semicircle is just the square root of x. All right, next, I want to know what is the area of the first cross section. So basically, what's the area of the very, very first semicircle? So if you remember, the formula for the area of a circle is pi r squared. In our case, since we are talking about diameters, I think of it more like, okay, so I have pi times, to find the radius, I have to take the diameter divided by 2, and then I square that. So this is for a full circle. If I want just the area of a semicircle, I just have to take half of that. So I have half of pi times the diameter divided by 2 squared. All right, so if I know that, I can now plug in what my diameter is. My diameter, we said, was the square root of x, right? So I'll have 1/2 pi times the square root of x divided by 2 squared. Now I'm going to simplify this, so I'll go ahead and square that. That would give me x over 4, and then I have to take 1/2 times that, and that's where I get pi x over 8. So that is the area of the first cross section. So I know that my shapes start at x equals 0 and end at x equals 2, because I have to have a start and an ending point. So I know it starts here and then it ends way over here at x equals 2. So I'm trying to find that, that volume of that shape. So I know to find the volume, I have all of these circles, circle areas, semicircle areas, that I want to just add up. So my volume would equal the sum of the areas of the infinite number of semicircles. Remember when we were doing Riemann sums and stuff, we wanted to decrease the width of our rectangle in order to be able to find the area under the curve. Same concept here, it's just we're finding volume. So we want an infinite number of these semicircles to be able to fill this all up as a solid that we're finding the volume of. So if I can find the volume of just one semicircle and I add up all of those semicircles together, that would give me my total volume. So if you remember, we defined an integral as the infinite sum of the areas. So my volume would equal my integral from 0 to 2 of the area of my first cross section. So that's going to be this pi x over 8 dx. So I can consider this pi over 8 as a constant. So I'm really just anti-differentiating x dx, which gives me 1/2 x squared evaluated from 0 to 2. All right, so that would be pi over 16 times 2 squared minus pi over 16 times 0 squared. So I get, this is 4, so I get pi over 4 units cubed. So that would be my volume. All right, let's try another one. This time, we're going to find the volume of the solid that lies between planes perpendicular to the y-axis this time at y equals 0 and y equals the square root of 2. The cross sections are squares perpendicular to the y-axis and run from x equals y squared and x equals 2. So if I sketch this region, x equals y squared looks something kind of like this. X equals 2 would be the line here. Oh, and we're going from y equals 0, so that's here, to y equals the square root of 2, so that would be up here. So my rectangles would look something like this when we're looking at them. Maybe it's easier if I look at them sideways so we can see them all, because they get smaller as it goes. All right, so I want to keep in mind the shape of my cross sections are squares. And then each of these little rectangles inside here would represent, oops, I drew that wrong. Each of those rectangles would represent the base of the side of the square. If I look here, this base here of the side of the square. So I need to find the length of one side. I need to find out what this length is. So to find the length of a side, basically I have to take 2, because that's as far this way as it comes, minus, because I take right minus left, so 2 minus the square root minus y squared. And the reason why I'm saying it's 2 is because if I'm going from y equals 0 to y equals the square root of 2, I'd have x equals 0 squared and the square root of 2 squared is 2. So that's where we're getting this from. So then to find the area of the cross section, it's just a square. So I can take 2 minus y squared and square that. So I get 4 minus 4y squared plus y to the 4th. And then my shapes start at 0 and end at the square root of 2. So to find my volume, I just have to do my integral from the 0 to the square root of 2 of my area, 4 minus 4y squared plus y to the 4th dx. So now I anti-differentiate. I get 4y minus 4/3 y cubed plus 1/5 y to the 5th, evaluated from 0 to square root of 2. So now I plug everything in. 4 times the square root of 2 minus 4/3 times the square root of 2 cubed plus 1/5 times the square root of 2 to the 5th minus 4 times 0 minus 4/3 times 0 cubed plus 1/5 times 0 to the 5th. So here I get 4 root 2 minus 8/3 root 2 plus 4/5 root 2, and then we have minus 0. So all together, this would give me 32 root 2 over 15. And that's it.